In this video, we're going to look at what happens to systems at equilibrium, focusing on things that have acids and bases. So here's a question. You should have it on your note sheet. So take a minute, pause the video right now, read the question, and choose what you think the answer to this question is. Alright, let's take a look at how you did. Now looking at this thing, you see we have nitrous acid with a pH of 1.5. And we think, alright, well, sodium nitrate, what would that do to the pH? Well, sodium nitrite, we might think, well, it's not an acid, doesn't sound like a base to me, so it might not do anything. Well, let's take a closer look at the situation. Now, if we look at who's involved, we have a beaker of nitrous acid. Now, you should know that nitrous acid is a weak acid, which means that most of it will be undissociated in the beaker. So we can look at our beaker here and see that most of the hydrogen and nitrite ions are still connected to each other and bonded. A small fraction of them have dissociated, so there's a small fraction of hydrogen and nitrite ions floating around in here separately. Now keep in mind, the question is asking about pH. So in terms of pH, it is only the undissociated hydrogen ions that affect the pH. These hydrogen ions that are still connected to the nitrite do not affect the pH. Alright, now let's take this acid and we're going to mess it up a little bit. We're going to add some sodium nitrite to it. Okay, now before we do that, let's consider the equilibrium reaction that's happening. I always like to write equilibrium equations. In this case, our weak acid is dissociating only partially, and there's my equation for that. So now we're going to go ahead and add the sodium nitrite. Of course, sodium compounds all dissolve, so I expect all of this to dissolve when I put it in my solution. And let's think about, well, what effect would that have on the equilibrium that's going on, and subsequently, how would that affect the pH? So, looking at the things that we just added, one of the ions that we just added is sodium. Okay, well, sodium's not really an acid or a base. Technically, it's a ridiculously weak acid, but it's not really ever significant in that sense. So, we can just ignore sodium as a spectator. We'll take him out. Now, the other ion that we just added was nitrite. Now, this is a little bit more interesting because there was already some nitrite in the situation. In fact, there was an equilibrium going on. We have our equation over here that had nitrite in it. We just added some more. So we want to think, well, will this have an effect on equilibrium? Well, hopefully this guy came to mind, Le Chatelier. You remember him talking about messing up equilibrium. So we now have messed up the equilibrium. We basically have added some more of that nitrite, which means it is no longer at equilibrium. But as Le Chatelier says, weebles wobble but they don't fall down. The system's going to regain equilibrium. But right now, it has too much product because we just added some of that. So to get back to equilibrium, it's going to have to shift to the left. That reverse reaction will have to kick into gear until it gets back to equilibrium. Now, in the process of getting back to equilibrium, let's think about what happens to our concentration of hydrogen ions. Well, when that reverse reaction kicks into gear, the concentration of hydrogen ions is going to go down. So my pH will actually be affected by adding what sounded like some harmless sodium nitrite, but it actually, by messing up that equilibrium, shifted it to the left. Now this is known as the common ion effect because we just added a compound, the sodium nitrite, that had one of its ions in common with an ion that was already in a solution. So it's usually referred to as a common ion effect, but it's really just a specific example of a case where you have Le Chatelier's principle, where in this case you're just adding some extra product. You're just focusing on the part of the ion there. So the official common ion effect rule is written out this way. It says the amount of a weak electrolyte that will dissolve in water is decreased by adding a strong electrolyte that has an ion in common. And we just saw an example of that because by adding that electrolyte, you're basically creating too much product, and so the equilibrium has to shift to the left in order to regain equilibrium. If you look at this table you have on your sheet, this is a good example of this. If we had 4 beakers of just straight 0.1 molar acetic acid. Now just plain 0.1 molar acetic acid by itself has a pH of 2.89. But if I added a compound, maybe some sodium acetate, well, in the sodium acetate, all of that will dissolve, so I'm essentially adding some acetate ions to that. Well, that's going to mess up the equilibrium. See, here's the equilibrium that exists within acetic acid down below here in the blue. And when I add sodium acetate, I'm adding some of those acetate ions, which means I'm messing up equilibrium, which means, again, it has to shift to the left, which means the reverse kicks in, which has to use up some of the hydrogen ions. And so my hydrogen ion concentration will go down. And so in this case, that means it is going to become less acidic. So instead of a pH of 2.89, it now has a pH of 4.44. And as we add more and more of that acetate ion, you see it has to shift farther to the left, so it becomes less and less acidic as we do that. Again, that's the common ion effect. Okay, question number 2 for you. Take a look at this on your sheet, pause the video, commit to an answer, and then hit play when you're ready. Alright, so in this case we've got calcium fluoride dissolving, doesn't dissolve very well. In plain water, 0.0031 grams will dissolve, but what happens if we try dissolving it in a liter of sodium chloride? Will that mess things up or not? Well, if you were looking at it thinking, well, I don't see any acids or bases, I don't see any kind of reaction happening, I don't see any common ions, I don't think it's going to have an effect, then you are correct. Okay, since we've got nothing going on there, no common ions, it doesn't matter whether I'm dissolving it in a liter of plain water or a liter of sodium chloride, I'm still going to have that same amount, 0.0031 grams dissolve. Now let's change that question slightly. Look at problem 3 on your sheet. Pause the video, think carefully about it, circle an answer, and see how you did. Alright, now this is a little bit different situation here because now, if I'm looking at this one, I do have a common ion. I had calcium ions already in the beaker, and I'm adding some calcium ions to it. So we want to see if this will affect how much will dissolve. Well, I've got to consider the equilibrium that's happening first of all. And you might say, well, who do I look at? Do I look at the calcium nitrate? Do I look at the calcium fluoride? So an important first question to ask yourself is, well, of these two components here, the calcium fluoride or the calcium nitrate, which is the weakest electrolyte? In other words, which will dissolve the least? Well, calcium nitrate, that's a nitrate, and I've memorized that all nitrates are very, very soluble, so I expect that to dissolve fully. But the calcium fluoride, in the question, it even tells us that it is only slightly soluble. So that means the calcium fluoride is my weakest electrolyte. So the first thing I'm going to do is I'm going to write the dissociation equation for my weakest electrolyte. So there's my calcium fluoride. When I put that in my water, only a little bit of it's going to dissolve. Now I want to think of what happens in terms of that equilibrium expression. So since I'm adding some calcium nitrate to that, I'm basically adding additional calcium. Well, that messes up equilibrium. So that means in order to regain equilibrium, it's going to have to shift to the left, which means that in that situation, less of the calcium fluoride will dissolve. Okay, some of it might actually precipitate out in that case. So again, the presence of the common ion, that's what it means by that statement, will decrease the amount of a slightly soluble salt that can dissolve. By adding more calcium to it, less of the calcium fluoride is able to dissolve. So if we look back at our original question, in pure water, 0.0031 grams could dissolve, but in the calcium nitrate, since there's already some calcium ions there, it's going to shift the equilibrium to the left, which means less than 0.0031 grams. So if you got that question right, give yourself a pat on the back. Good job. All right, another question for you. Again, pause the video, think about it, see what you said. All right, let's see how you were thinking on this one. Now again, in looking at each of these choices here, you notice we do have some common ions to the calcium sulfate. Our first example here has calcium ions in common. Again, I started by writing the dissociation. This is slightly soluble, so there's my ions that are present in the equilibrium going on with that. And if I introduce this into some calcium ions, I have some calcium ions in common. In fact, in 1 mole of calcium nitrate, there's exactly 1 mole of calcium ions that are in that, in a 1 liter of that. Number 2, now there's no calcium in there, but I have sulfate, which is also in common. And again, if I had 1 liter of 1 molar sodium sulfate, thinking about the formula for that, that means I have 1 mole of sulfate ions in common. So these two will both have the same effect. Since this has 1 mole of additional product and the other one has 1 mole of additional product, I would definitely expect less calcium sulfate to dissolve in both of these guys than I would to expect to dissolve in just plain water. However, I would expect the same amount of calcium sulfate to dissolve in both number 1 and number 2 because they both have that 1 mole of extra product added to them. But let's look at number 3. Now, hopefully you wrote the correct formula for ferric sulfate, and we can see in this case if I have 1 mole of ferric sulfate, well, for every mole of that dissolves, I'm actually going to get 3 moles of sulfate ions. So even though the concentration looks the same, I actually have 3 times as many sulfate ions, and so if we add 3 times as much sulfate, that really messes equilibrium up. It's got to shift way farther to the left to regain equilibrium, and so that means a lot less of it will dissolve. So pure water, there's no common ions there. So the most calcium sulfate will dissolve in pure water. There'll be a little less that can dissolve in number 1 and number 2, but number 3 was the answer to the question. The least calcium sulfate, only a little bit of it will dissolve in the ferric sulfate because it has much more of the common ion. All right, let's look at another example. Read this question, pause the video. You know the drill. All right, now hopefully this situation sounded familiar to you because we actually did this in our equilibrium lab that we did. So we had our sodium chloride solution, and when we added the acid, hopefully you remember that it got cloudy. And the reason why is there was our sodium equilibrium. Now normally we write a single arrow when we're dissolving sodium chloride in water because it's all soluble, but if we have saturated it, we've maxed it out, so it's actually an equilibrium situation then. Well, if I add hydrochloric acid, well, there's a common ion, that chloride ion. So again, adding more of the product, it's going to mess up equilibrium. It's got to shift to the left. The reverse reaction has to kick in to get back into gear, which means my amount of salt that can dissolve is now less. So I had a supersaturated solution. So some of that salt will precipitate out, and that's what causes that white cloudiness. So 3 was the correct answer for that one. Now let's look at another question, and this one is a little bit more quantitative. So here we've got here we have hydrogen fluoride, and I'm mixing that with hydrogen chloride. So I have a situation where I have a common ion, the hydrogen ion here. So I want to think, well, what's my frame of reference? What equilibrium equation do I think of? And remember, the question is, which of these guys is the weakest electrolyte? Well, hydrochloric acid, of course, is a strong acid, and the HF, that is a weak acid. So that's my weak electrolyte. So I want to first write my equilibrium equation in terms of the HF. So there's the equilibrium that I'm thinking about, and that's my primary equilibrium system that I'm paying attention to. There's my equilibrium expression. Since this is a quantitative question, that might come in handy. Now, of course, another deal here is if I look at my equilibrium expression, there are a couple of variables that I do not know. So, of course, icy chart to the rescue here. We're going to set up an icy chart to help us answer this question. Again, this is my main equilibrium system going on, so I'm going to set up my icy chart in terms of this equation. So there's my icy chart there. Now, initially, we've got 1.2 as our concentration of HF, and if we look at this now the HF, initially from the HF dissociating, I have 0 fluoride and 0 hydrogen ions. However, in this problem, there's another source of hydrogen ions. So none of the hydrogen comes from the HF initially, but I've got 0.1 molar HCl to begin with, and since that is a strong acid, that means I'm going to have 0.1 molar of hydrogen ions. So I'm going to write that in as my initial. That's where this is a little bit different than our other problems, because without the HCl, this would have just been 0, but we are adding the 0.1 molar HCl. Now my fluorine still is 0 because that's coming when this dissociates, and initially none of it has dissociated. Okay, I write my change in, everything's just 1-to-1 ratio. My equilibrium equations, I can write those in. And so, well, what's this going to be at equilibrium? Well, right now I don't know. However, remember our little trick that we can use. Since HF is a weak acid, how much am I going to have at equilibrium? Well, only a small amount dissociates. If we look at our 3 powers of 10 rule, My initial concentration goes to one place. My power of 10 is to the 4. There are 3 powers of 10 different. That means the amount that dissociates is going to be insignificant. So we can assume that there will be approximately 1.2 molar concentration still of that at equilibrium. Now, as far as my hydrogen ions go, this is another tricky one here because I started with 0.10 molar. Now I'm going to gain some when some of this dissociates. But again, since this is a weak acid, only a small amount of that is going to dissociate. So my X value is going to be very, very, very small. So we can take a little guess assumption that probably is not going to change. And we can go back and check that after we're done. But for right now, we can still make that assumption, again, because this value is quite a bit smaller. Might not quite be a full 3 powers of 10 difference, but it's pretty close. And then, of course, my fluorine, that's what I'm trying to find in this question. So I write my equilibrium expression. I pop my values in from my IC chart. There's the 1.2, the 0.10 molar. We solve it for X. And again, there's just my work for doing that. So we come up with an answer here of X is equal to 8.2 times 10 to the negative third. And remember, we had set X up as the concentration of the fluoride ions, which was actually the answer to one of the questions. Now, in addition to that, the question also asks us what the pH would be. And in this case, my pH is simply equal to my hydrogen ion concentration, which is going to be, that actually should say 0.1. And 0.1, now X was 0.0082, but as we thought, that amount is actually insignificant compared to our 0.1. So again, this should say 0.1 plus 0.0082. When we round it to sig figs, we still get 0.10 molar as my concentration of hydrogen ions. So taking the log and the opposite of that, we get that the pH is going to be 1. We're going to look at one last problem here. And in this case, you can take a minute. Now what I would do is I would pause the video and see if you can do this one all on your own. This is very similar to the last question. You should be able to solve it. When you are ready, you can play it. I'll work through the solution. You can fast forward and stop and pause as needed. Alright, so to solve this, the first question I ask myself is, who is the weakest electrolyte? I've got 2 substances. I've got ammonia and I have ammonium sulfate. Well, ammonium sulfate, ammonium compounds, I know ammonium is one of my super-soluble ions, so I expect that to fully dissolve. And ammonia, of course, I know is a weak base. That means that is the weak electrolyte. So my equation that I'm thinking in mind the whole time is the equilibrium of the ammonia. And since ammonia is a Bronsted base, remember when I write my dissociation equations of the Bronsted bases, I always include water to show where my hydroxide is going to come from. So this is the primary equilibrium system that I am thinking of. Again, the next step here, there was a lot of stuff I didn't know, so I'm going to set up an IC chart. What are my initial conditions? Well, my ammonia concentration initially is 0.25 molar. Pop that in. Okay, initially, none of it dissociates. So initially, I have 0 hydroxide from the ammonia. And now, none of it makes NH4. However, I have another source of NH4. Okay, we have the ammonium sulfate that we're putting in here. So I have to figure out what my concentration of the ammonium ions would be from the ammonium sulfate. So we have to do a little work to do that. There's my formula for ammonium sulfate. It dissociates. There's my work for how I figured out what my concentration would be. It turns out that 1.7 grams is 0.013 moles of ammonium sulfate. And again, for every 1 mole that dissociates, I get 2 moles of ammonia. So 0.013 moles of ammonium sulfate gives me 0.02 moles of ammonia. Popping that into my molarity equals moles over liters formula, I get 0.069 as the concentration of ammonia initially. So we can pop that 0.069 into our IC chart. We can write in our changes, write in our equilibrium expressions, and again, what are my equilibrium concentrations? Well, again, we can use our tricks. Since this is a weak base, the amount that dissociates is going to be insignificant. We've got our 3 powers of 10 rule. This goes to 2 decimal places. My KB value for this is 5. It's 3 powers of 10 separation. So we can be quite safe in assuming that it still is going to be 0.25 molar at equilibrium. Same thing for the ammonia. And this is a little more of a guess. Again, we can go back and check this. But the amount that we're adding to our initial 0.069 is X. Well, because this is such a weak base, X is going to be very, very small, and most likely when I add it to 0.069, probably won't change that number. Not 100% sure if that's going to affect it or not, so I'll put a question mark by it. We can come back to it later after we figure out what OH is and see if that changed it. So now working this problem out, I write my expression. Again, this is my main equilibrium reaction we're considering. There's my equilibrium expression for it. The problem gave me my Kb value, so I plug that in. From my IC chart, I'm just plugging my equilibrium concentrations in. I do not know my concentration of hydroxide, so that's what I'm solving for. So rearranging this equation, I come up with an equilibrium concentration of hydroxide as 6.5 times 10 to the negative fifth. So that's what X is. And earlier in IC chart, we had our question mark. We had our 0.00 or 0.069 plus X. Well, if you add 6.5 times 10 to the negative fifth plus 0.069, and then round your answer to sig figs, it does not change it. So our assumption there was correct and safe. Now we want to finish answering the question. The question asks, what will the pH be? So we just have a little bit more work to do. We're almost done down the home stretch here. To calculate the pH, well, there's my formula. I know the hydroxide concentration, and so all I can do is pop my hydroxide concentration in, do my work there. So my pH, or my pOH comes out to 4.2, and of course remember this nice easy formula here. If my pOH is 4.2, I just subtract that from 14 and we get a pH of 9.8 as the answer to the question. So really these are just an extension of equilibrium expressions and equilibrium questions that we can do here. So bottom line, common ion effect. If you are adding a compound, and if that compound you're adding has an ion in common with one that is already present in your equilibrium solution, it's going to reduce the amount of dissociation that would happen. Okay, if it was something dissolving, it will reduce how much was able to be dissolved. For example, we did the calcium sulfate problem earlier. So if I add another compound that has the calcium ion in it, and if it dissolves, adding the presence of those calcium ions is going to reduce how much of the calcium sulfate will dissolve. Common ion effect, but really it's just Le Chatelier's principle. Thanks for watching. Hope that helped.